In this video, you are going to learn pressure, a chapter of IGCSE O-level Physics. You will be able to accomplish a firm grip on the concepts related to pressure. I'm an experienced online physics tutor and I've done thorough research on these concepts of IGCSE Physics. So, let's begin pressure, our 7th chapter of O-level Physics. Let me define pressure first. Pressure is the force acting per unit area on an object. So, pressure is equal to force per unit area. The SI unit of pressure is Newton per meter square, and Pascal is another unit of pressure as well. Okay. Now pressure will be in all states of matter: solid, liquid and gases. In order to find out the pressure in solids, we will be using this formula, force per unit area. Let's suppose there is a box or there is a block of an area. This is the area A of the block, and the weight of the block is basically the force. So its pressure on the ground will be weight over area, or force per unit area. Okay. Moreover, I give you some examples of pressure. Let's suppose needle. I draw a needle like here, like this. This is the tip of needle. This tip has very small area. If we apply a significant force over here, or like some small force over here as well, then pressure will be way more pressure. So in order to increase pressure, we could increase force, because pressure is directly proportional to force, or we decrease the area because pressure is inversely proportional to the area. Another example, let's suppose someone wears high heels like this. I draw a sketch of high heels. Okay, and someone wear flat shoes with this much of area, and it has this much of area. Now over here the area is less, pressure will be more. And here area is more, pressure will be less. So in solids, you should keep this formula in your mind: pressure is equal to force over area, these units in your mind, and this relation of pressure with force and area. Now we will discuss the pressure in liquids now. Pressure in liquids. How pressure behaves in liquids. Let's suppose I fill this vertical cylinder with water. These are the narrow openings. Okay, there is a sink over here. Now when the water will exit from this vertical cylinder, the pressure will be like this. This middle one has moderate pressure, and this upper one will have least pressure. Okay, now what is being happened here? We can see the pressure depends on the depth of the liquid. The more depth a liquid have, the more the pressure. Moderate depth, moderate pressure. Least depth, least pressure. So the distance from the top of the water and to this opening is H1. The distance from top to the second opening, it's H2. And the distance from top to this third opening, that is H3. Now you can see H1 is greater than H2 and H2 is greater than H3. The pressure from the hole 1 is greater from hole 2 and the pressure of hole 2 is greater than hole 3. So from this diagram we can deduce that pressure in liquid is directly proportional to the height or depth of the liquid. Now what will be the formula for the pressure in liquid? The formula will be pressure is equal to rho GH, where this rho is the density of the liquid, this G is the gravitational acceleration, and this H is the depth of the liquid. Okay, so this will be our pressure, the definition of pressure, the formula of pressure in liquids. Now what if we have to measure the pressure, the atmospheric pressure, the pressure on our atmosphere? How will we measure the pressure, the atmospheric pressure? Measuring atmospheric pressure. We measure atmospheric pressure by using an instrument called barometer. You can memorize this instrument. It might come in your MCQs. Barometer. So how does a barometer works? There's a sink and a tube over here. This sink is full of mercury. Okay, and there is vacuum in the tube in this area. When atmospheric pressure exerts on this mercury level, the level rises till here. Over here there is atmospheric pressure. I write it as P ATM in subscript. Okay, so after the application of atmospheric pressure, we can measure the length from the surface of mercury to the surface of mercury in this tube. Let's suppose this length is H. So by using the formula for the pressure in liquids, P is equal to rho GH, we find the atmospheric pressure. Here the density will be used for mercury. Rho is the density of mercury. G is gravitational acceleration. H is basically the depth. So pressure is equal to rho GH, and the atmospheric pressure is after the measurement from this experiment is 1.013 into 10 raised to the power 5 Pascal. This is basically the atmospheric pressure of a liquid. This is the atmospheric pressure of the air at the sea level. One more question. We write atmospheric pressure as 760 millimeter of Hg. What does it mean, 760 millimeter of Hg? I told you that the liquid over here is mercury. Upon the atmospheric pressure, the height that was measured from these two levels, the difference of level that was measured after the application of atmospheric pressure was 760 millimeter. So when atmospheric pressure was exerted on the surface of the liquid of mercury, the mercury raised 760 millimeter above. That's why we say that atmospheric pressure is 760 millimeter of mercury, 760 millimeter Hg. So by using a barometer, we find out the atmospheric pressure at sea level or at any level on earth. Now, next thing is measuring gas pressure by using another instrument. Measurement of gas pressure. How do we measure the gas pressure? We use an instrument called manometer to measure the pressure of a gas. The manometer is like this U-shaped rod, like this. Okay, here the pressure of gas comes, and initially at the initial stage there is some liquid over here, because initially from here the pressure will be of the atmospheric pressure, and from here the pressure of atmospheric pressure. So from both the sides the pressure will be same, that is of atmospheric pressure. So these two liquids will be at the same level. Now after the application of gas, I draw a new figure. After the application of gas pressure, the level of the liquid rises from one end and decreased from another end. So the difference of height will be measured by a meter rule. Okay, and by using the formula P is equal to rho GH, we can measure the pressure of the gas on this side. Now you have to observe one more thing. Over here, from this side, the pressure is for gas only. So pressure of gas will be equal to this rise in length rho GH plus this atmospheric pressure, because this end is open, so atmospheric pressure will be also be acting on this end. Rho GH plus P atmospheric. So by using this formula you can find out the pressure of a gas using the instrument called manometer. Okay, now the next thing, Pascal's hydraulic press. It is basically the application of practical application of pressure Pascal's hydraulic press. What does it mean? It means that I told you pressure is equal to force per unit area. Okay. Now, what if there is a system in which on one side we increase the area and on other side we decrease the area? Let's suppose there is a system over here. There are two pistons. This is piston 1 and piston 2, and in this sealed rod or a sealed pipe there is incompressible liquid, a liquid that cannot be compressed on the application of when the pressure is applied to it. Now if we apply force F1 over here, and this piston has area A1. Let's suppose its value become equal to 10 Pascal. Now the pressure over here on piston 1 should be equal to the pressure over here on piston 2. So the pressure over here would be 10 Pascal as well, but here the area of the piston is way more than the area over here. So Pascal's hydraulic press principle says that when the pressure is applied on an incompressible liquid, the pressure will remain constant at both ends. So I give you an example. Let's suppose the area over here is 1 meter square, and the force over here is 10 Newton. So that's why the pressure is 10 Pascal. Now the same pressure should be over here. Now its area is 10 meter square. Now what will be the force over here? The force will be 100 Newton, and the pressure will be 100 Newton over 10. It will be 10 Pascal. So you see, the force has been increased 10 times just by increasing the area. This is basically the principle of Pascal's hydraulic press, that you can increase the force by increasing the area and the pressure will remain constant. This is the application that we see in the braking system of cars. In car lift, during washing of car. Okay, so this is basically the practical example of pressure, and this is Pascal's hydraulic press. You just have to keep in mind one thing: pressure on both ends will be same. Pressure on P1 is equal to pressure on P2. So you can find out the unknown terms in your questions. Now after Pascal's hydraulic press, we move on to pressure in gases. As I told you, in liquids the pressure is caused by the depth of the liquid. Now in gases, the pressure is caused due to the collision of molecules with the walls of the container. Pressure in gases. It is due to the collision of gas molecules with the walls of the container. Let's suppose there is a container, and this container there is gas molecules. It's a piston over here. Now the pressure exerted on the walls of the container will be the random collision of gas molecules with other molecules and with the walls of container. The more the collision, the more will be the pressure on the walls of the container. Now in gases, we are only concerned about the collision of gas molecules. If gas molecules have high kinetic energies, the collision will be more intense. If they have lower kinetic energies, the collisions will be less intense. So we have to see what are the factors that increase the collision of gas molecules. Let's suppose by increasing temperature, the kinetic energy of the gas molecules increases, hence pressure increases. By decreasing the volume, pressure increases because kinetic energy of the molecules increases. Moreover, by applying Yeah, two factors: by increasing the temperature or by decreasing the volume, the pressure of the gas molecules increases. Now we have to see some certain relationships between pressure and temperature, between pressure and with temperature, volume, and the relation of volume with temperature as well. So the relation between pressure and temperature, relation of pressure with temperature. Pressure is directly proportional to the temperature. If there is a container over here, its piston is at this position. When you increase the temperature by placing a Bunsen burner over here, then the pressure of the container will be increased. But over here, you should keep the volume of the gas constant. Then the pressure of the gas will be increased. The pressure is directly proportional to the temperature, while volume remains constant. Okay, so over here V1 is equal to V2. This was P1, this is P2, this is T1, and this temperature is T2. So in this example, the volume remained constant, but the pressure of the gas increased after increasing its temperature. Next relation, pressure versus volume. Pressure versus volume. The pressure of gas is inversely proportional to its volume, while temperature remains constant. Let's suppose there is a container in which there is some gas. It has volume V1. Now temperature is constant. Now if the volume of gas increases to V2 is greater than V1, then the pressure that was here P1, and then this is pressure P2, the pressure will decrease. If volume increases, P2 will become less than P1. Okay, this is because when the volume is increased, the collision of gas molecules with the walls of container decreased. When that collision is decreased, then the pressure will also decrease. Okay, so this is basically the relation of pressure and volume, inverse relation. Pressure is inversely proportional to the volume, and T, that means temperature, it is constant. Now the last relation, that is of volume and temperature. Here the pressure will remain constant, so volume is always proportional to the temperature. Let's suppose there is a container and there's our gas molecules, they have volume V1. In second stage you increase the temperature by placing a Bunsen burner over here, then the volume of the gas will increase. here the amount of gas, the collision of gas molecules with the walls of the container remains constant. That means pressure remained constant. P remained constant. Okay, but the volume has been increased. So here V2 is greater than V1 and T2 is also greater than T1, but pressure is constant. So you have seen in this terms that pressure is only concerned about the collision of gas molecules with the walls of the container. Okay, so these are the relation between pressure and volume, volume and temperature, and pressure and temperature. From here we can deduce that an equation like pressure is inversely proportional to the volume, or we can say pressure is equal to K over V, where K is a constant of proportionality. In first case, pressure is P1, volume is V1. In second case, after increasing the volume, pressure became P2 and volume became V2. When we compare these two equations, we come to a conclusion that P1 V1 is equal to K. Also P2 V2 become equal to K. So P1 V1 will be equal to P2 V2. So this is the equation that we'll be using in our questions in order to compare the initial pressure and volumes with the final pressure and volumes. So this is it for chapter 7 of IGCSE O-level physics, pressure, in which we studied the pressure for solids, liquid and gases. We discussed the instruments to use to measure the pressure like barometer and manometer. Moreover, we discussed the Pascals hydraulic press in this chapter. If you have any confusion regarding that you want to ask from me, just comment below in my video and I'll be answering all of your questions. Thank you.